and then we'll get started. Matt, is this looking good, the screen share?
Yep,
Yeah,
solid.
great. Okay, good. So let's start with the Big Bang. And, how do we know that every particle in our bodies is 13.8 billion years old? So the answer is that it came from a Catholic priest and a priest who proved Einstein wrong. His name was Georges Lemaitre, and he was a Belgian priest who went to seminary school, was absolutely always entranced by science, and with the permission of his cardinal, got permission to study relativity, first at the University of Cambridge and later at Harvard. And so in the 1920s, Lemaitre heard of some very hazy observations that suggested that the stars that were further away from Earth were moving away from us faster than the stars that are closer to Earth. And Lemaitre rewound time in his head and thought, well, if that's the case, then the universe might be expanding. And if the universe is expanding now, if you go back in time, the universe was smaller a little bit earlier. Earlier than that, it was smaller yet. And if you take that back far enough, at one point, the universe would have to be an infinitesimal point of space and time and energy. So he wrote a paper. It was completely ignored. The fact that he wrote it in French didn't help, but nonetheless, so he ended up tracking down Einstein at a very famous physics conference, and Einstein basically said to him, "Your physics is excellent, but your physical intuition is abominable." Einstein hated the idea. And when you think about it, it's pretty obvious why. If we accept the theory of what we now know as the Big Bang, that the universe started in a tiny little point, what did the universe expand into? And if that's the origin of time, what came before time began? So there are all kinds of crazy things that don't make sense to us, except that this is the theory that we're left with. So but Lemaitre was not dissuaded by Einstein, because he went back to the drawing board, and he spent quite a long time diving deep into Einstein's equations of general relativity. And he came out with a solution of that actually proved that this was a possibility according to Einstein's equations. And Einstein, to his credit, listened. He talked to Edwin Hubble and other people who had made more recent observations. And ultimately, he came around to accepting the theory that we know as the Big Bang. Although he was very reluctant for a long time, because it also smelled a bit of religiosity to him. Because here was a priest telling him that the universe began, with energy. It was too close to him to the biblical story of let there be light, that God had created. But in the end, Einstein came around, and in fact, it is one of the best supported theories of science that we have. So what happened to the Big Bang is that out of the Big Bang emerged electrons and some of the tiniest particles in our body, which are gluons, which are quarks, and gluons, which are particles that glue the quarks together. The gluons and the quarks create the protons and neutrons in our bodies that make our atoms. And so those formed in the universe the first 4 elements in the universe. Most of it was hydrogen and helium. And our bodies are 10% hydrogen, which means that 10% of the mass of your body was born in the Big Bang and still exists in that form today. And in fact, but the question then is, well, where did the rest of our elements come from? In fact, 98% of our elements is made of just 6. 98% of our body is made of just 6 elements. It's carbon, nitrogen, oxygen, phosphorus, and sulfur. But all told, we're made of about 25 essential elements. We have enough carbon to make about 25 pounds of charcoal in our body. If you're 150 pounds, you have enough salt to fill a salt shaker and enough chlorine to for several backyard swimming pools. So where do these other elements come from? That was for a long time a huge mystery. Cecilia Payne, who was a Harvard astronomer, was one of the people who set the stage for solving that problem. She was a fascinating character. She studied at the University of Cambridge. Actually, she was a contemporary of Lemaitre, and she fell in love with science. It was almost like a conversion to her. But she discovered that at the time, in the 1920s, she couldn't continue in science in the UK. The best she could do was become a headmaster at a girls' school. But she managed to finagle a scholarship at Harvard University. And there they had a huge collection of glass plates, which on which were photographed spectra of individual stars. And this is what they looked like. And Payne at the time was one of the few people, actually the only person at Harvard, who knew enough about the very new theory of quantum mechanics that she could apply that to analyzing these very, very faint stripes on the plates, which represent the different elements in them. And each of these little tiny hand notations represents, iron or chlorine or sulfur or a different element. And she found something that nobody wanted to believe, and nobody did actually believe for a while. She found that 98% of stars, people had believed that stars had the same composition as Earth. So not only did they have the same elements and the same percentages as Earth, but they believed that stars had huge iron cores in the middle, just as Earth does. Payne showed that stars are 98% hydrogen and helium. Most of it actually not hydrogen. And in fact, when she presented her results to the world's greatest expert in America on stars, he told her results could not possibly be right. And she ended up accepting that as very likely true, although she later regretted it, and writing in her thesis, which was considered one of the finest theses in astrology's ever written, astronomy rather, that she ended up writing that particular part of her results was almost certainly not true. But a few years later, it was discovered from other evidence that in fact it was true. So now all of a sudden we knew that stars were mostly made of hydrogen. So then how were the stars created? I'm sorry, how were the elements created? So the next person to pick up the research was a brilliant physicist by the name of Fred Hoyle. And Hoyle was sure that stars must make the elements, and he didn't know how. And the problem was that everyone claimed and everyone believed, for many reasons, that stars could never get hot enough to create other elements. But Hoyle, with some colleagues, was able to show that in a star, which is made by the condensation of hydrogen and helium, when the gravity pulls it so tightly together, hydrogen fuses into helium and gives off heat. That's what our sun does. That's how we get energy here. And Hoyle was able to show that heat got large enough that the star grew and got hotter and was able to create more elements. It was able to create carbon, and it was able to create oxygen. And as it did and got hotter and hotter and larger into what's called a red star, a red giant star, that process creates all of the elements in the universe up to iron. After that, what happens to create the rest of the elements is what you see in this photograph. This is a photograph from the Hubble telescope of the most powerful kind of explosion in the universe. It's a supernova. It's where a star gets so hot that it literally explodes. And in that explosion, it creates all of the heavier elements, all of the elements with the higher atomic numbers. So all of the elements in our body, with the exception of hydrogen, literally came from stars. And that's, of course, what Carl Sagan meant when he said, you are star stuff, or what Joni Mitchell, said when she said, we are stardust. Is that literally, that's where the stuff in our bodies came from. So what you had then, and we're kind of like walking through the evolution of the universe, and in a sense, is what you had is huge clouds of elements floating out in space. And when great concentrations of them collided, you had, again, enough hydrogen and gravity acting to create new stars. And that's how our solar system was created. There was a star in the middle and a ring of debris circling it. And all the tiny dust from all those those elements collided and collided and collided and created larger and larger rocks and boulders and mountains. Ultimately, what you got was the formation of the 9 planets through huge cataclysmic collisions. Of course, all the elements in our body were there at the time and were part of these collisions. And many of you may know that the last and largest collision for Earth was when a Mars-sized body smashed into Earth, which was 90% of its current size, and created the moon. The impact was so large that the debris went back into space, and enough of it coalesced in the atmosphere in orbit around the Earth to create the moon. So here we have a inhospitable Earth, but we have planet Earth 4.6 billion years ago. But life is made from organic compounds. And those are long chains of carbon and hydrogen, hydrogen, oxygen. Those are the carbohydrates and the sugars in our body. You won't find those, you won't find organic compounds in any rocks. So the question of how life arose has long been a great mystery. And many of you may have remembered that one of the first explanations was by a scientist named Stanley Miller, and he proposed that there were gases in the Earth's ancient atmosphere, somewhat like here, and the energy from lightning or UV rays made those gases create organic molecules that fell down into ponds or pools of water on Earth, and that's where life started. But there was a problem with that theory, and the problem was it turned out that the gases that he suggested were in the Earth's ancient atmosphere actually weren't. And so then for a long time, actually, people were really stumped as to how to begin to explain the origin of life at all. And then there was a new discovery, an accidental discovery, that changed the way people thought about it. And I'm going to just read you a short passage from my book, because this discovery also illustrates, and I found this so many times in chronicling many of the discoveries in my book, it also illustrates how often scientists were looking for one thing and they found something completely different. So the scene is about 300 miles off the Galapagos, and the National Science Foundation in 1977 sent a huge research vessel and the submersible called the Alvin there to look for hydrothermal vents, which are hot springs at the bottom of the ocean. The reason they were looking for them is there was a new theory called continental drift that was controversial. They were looking for evidence to support it, and the um, the actual discovery of hot vents under the ocean would support the theory. So I'm going to read you a little bit of what happened next. At dawn on February 17th, Jack Corliss, who was the leader expedition, the geologist Tjeerd van Andel, and the pilot Jack Donnelly climbed down the narrow conning tower into the Alvin. They crouched by the small portholes and prepared for a descent of 1.7 miles in the titanium submersible, built to withstand pressures of 9,000 pounds per square inch. They went down 1.7 miles, and at last they reached the bottom. In the first moments, their searchlights illuminated only black flows of pillow lava formed when cold seawater met molten rock. But then they saw something no one else had ever seen. Though the water nearby was almost freezing, they saw cloudy blue water shimmering with minerals rising from the ocean floor. They would learn that the temperature in some places was a balmy 63 degrees, comfortable enough to enjoy without a wetsuit if it weren't for the crushing pressure. They had for the first time found a hydrothermal vent. Looking through a porthole, Corliss saw a sight that forever impressed itself in his memory. Using his acoustic phone, he called his graduate student, Debbie Stakes, on the research vessel above. "Deborah, isn't the deep ocean supposed to be like a desert?" Stakes took a moment to consult her fellow geologists. "Yes," she replied. "Well, there's all these animals down here," he said. He was gazing at clams as wide as dinner plates, giant mussels, albino lobsters, and orange and white crabs. This is an image of some of the things that they saw, not from his actual expedition, but from others that were taken soon afterwards. It made no sense. He was over 8,000 feet down, cut off from all sunlight and food from above. Frantically, Corliss and von Andel scrambled to collect data and capture a few specimens with Alvin's robotic arm. The next dives revealed more vents and more creatures even more outlandish. Spaghetti-like worms, large pink fish, and 7-foot tube worms with red plumes swaying languidly like flowers. Back on the RV Noor, the scientists examined their finds with wonder. Kathy Crane, the expedition's navigator, radioed biologists at Woods Hole to ask for help in identifying the strange creatures. They couldn't. The startled geologists, and I have to make the point here that the expedition was geologists and engineers, and that was it. There was not a single biologist on the actual expedition itself. The startled geologists had little to preserve the specimens with, except a small jar of formaldehyde a graduate student had bought and some Russian vodka that they purchased in Panama. They would have to store the creatures in Tupperware and plastic wrap. Sometime later, one of the expedition leaders received a message from Woods Hole. The telegram said, "Return home to port instantly. Biologists coming." Needless to say, Corliss did no such thing. He had no intention of being scooped. So, again, the idea that life might have formed at the bottom of the ocean never occurred to anyone until this very important discovery. Since then, there are a great number of scientists who believe that that's where life may have first arisen, because that's where organic molecules may also have first arisen. There is another theory, which was the work was rather made possible by the work of Charles Townes, who was a brilliant physicist. And Townes wondered whether organic molecules might have actually formed in the clouds in space and fallen somehow down to Earth. everyone thought this was impossible because space is, in fact, it's got X-rays and UV rays and other particles that would destroy any long, delicate chains of organic molecules. But Townes figured out a technology, a way of looking for them. And when no one else would do it, he took his Nobel Prize money and he built the transmitter and set up the microwave telescope to look for them. And within days, he had found an organic molecule in space, which is, pretty amazing. This is actually an actual image of hydrogen cyanide, which is an organic molecule of hydrogen, carbon, and nitrogen from an actual star, and emitted from a star. And now we found that there are over 200 types of organic molecules that we've detected in space. And so there are now scientists who believe that life probably did arise at the surface of Earth. And quite a number of them believe that it may have been because some of the molecules from space through comets or asteroids or drifting on tiny bits of dust found its way to Earth's surface. And those were the organic molecules that first created life. So this is one question, how life evolved, that we don't have an answer to. We've got a lot of very compelling theories, but as yet there's quite a divide between people who suggested life evolved on the surface of Earth and those that suggest that it evolved deep beneath the waves. So we're now about 4 billion years ago, give or take, when we have the first life. And the first life is bacteria in the ocean. There's no life on land. It's bacteria and other kinds of single-celled organisms. The continents are barren. And there would be a problem for you and me if we went back there. And the problem is that there was no oxygen. So our atmosphere today is, we have 21% oxygen in the atmosphere. And obviously we breathe, we need it to breathe in order to live. So the question is, how did that oxygen get in there? And the answer is these remarkable bacteria called cyanobacteria, which evolved to photosynthesize. And, when I was in high school, I thought photosynthesis was the more boring thing in the world. Now I think it's one of the most amazing things in the universe. It's just incredible, because what is photosynthesis? Creatures like the cyanobacteria take carbon dioxide that's floating in the air. They take hydrogen from water. They use energy from the sun, which is 93 million miles away. And out of that, they make sugar. And that sugar can be used for energy, and it can be used to make other molecules with. And so cyanobacteria both began to introduce oxygen to the atmosphere, and some of that oxygen, by the way, floated up into the high levels of the atmosphere and created the protective ozone layer, which also allowed us in the end to be able to survive on land. What that means is, if you look at a tree is actually 99% a product of photosynthesis. 94% of a tree is made of carbon and then this is the dry mass of a tree, is made from carbon and oxygen that was plucked from molecules in the air. And about 6% of a tree is from water. And with the oxygen in the atmosphere, more complex cells that have mitochondria that could burn sugar to liberate energy evolved. Those are called eukaryotic cells. And animals are made from that cells, that we get our energy by having mitochondria in our body, which burn sugar with oxygen to release energy. But we too are ultimately products of photosynthesis. 93% of our dry mass is also from carbon dioxide molecules that were once floating in the air. And much of the rest of it is also from hydrogen. 10% of it is also from hydrogen. we are very, very much products of those plants and the way in which life and photosynthetic organisms completely transformed our planet, our atmosphere, and of course that allowed plants to spread onto the land, and it allowed the ecosystem to grow up that made it possible for us to to exist, both because there's oxygen in the air and because there's food to eat that the photosynthesizers create. But how is it that those particles and molecules in our body create life? Well, of course, there's DNA, and there are many processes, and I talk about quite a number of them in my chapter. But one of the interesting stories is that is the story of a scientist by the name of Albert Claude, who was a Belgian scientist, who was faced with a real puzzle, and that was that he was desperate to learn the answer to that question because his mother, when he was young, died of cancer. And he wanted to know what was going on in his cells. And the problem in the 1920s was that if you looked at a cell in a light microscope, all you could see was a nucleus. You could see some structure that was called a mitochondria, and no one knew what it did. And then there was another structure called a Golgi apparatus, and people even questioned whether that was just an artifact of the staining process. But Claude who was determined to see if he could figure out what was going on in the cell. The only other thing you could see was just this gray mass. And biochemists were quite convinced that they knew what was in that gray, indistinct stuff there. And they were sure that it was enzymes that created life in our cells by catalyzing chemical reactions. Enzymes are the proteins that very, very quickly make chemical reactions happen. And they were convinced that that was how life was created. Claude was suspected that there may be some kind of structures. And so the first thing he did was he used an unlikely tool called a high-speed centrifuge. If you grind up cells and you put them in a centrifuge and you whirl it around very quickly, he found that the liquid separated into layers. And when he spun it again, it separated into more layers. And he looked at those layers under the microscope. He saw teeny tiny objects in there. Now, many people said, "You're just crushing cells. What are you doing? This is, you're not finding anything meaningful." But he was convinced that there were structures there. And he was lucky enough to be in New York City in the 1940s when the first electron microscopes came around. And so he was the first, with his colleague Keith Porter, to examine an animal cell under electron microscope. And for the first time, he was able to see, in fact, that there were structures. And we now know, that there are organelles, there are ribosomes that make proteins, there are mitochondria that burn energy, there are Golgi bodies which package proteins and send them all over the body. There are lysosomes, which are like the cell's trash disposal units. There are microtubule highways throughout the cell and little machines that call vesicles behind them. In fact, our cells are crammed with an astonishing array of nano machines, all kinds of nano machines. And one of the most interesting, my favorite, was discovered by two people. One was an iconoclastic biochemist named Peter Mitchell, and then his work was built on by another scientist named Paul Boyer. And what they discovered was this machine here, which is called ATP synthase. So this is the machine, the little nano machine inside our mitochondria that creates ATP. ATP is the energy currency in our cell that's used for all the energetic reactions in our cells. And this thing it's got a rotor that spins at 300 times per second. It can spin that fast. It can even go backwards. And it's powered by electric currents of protons created by the Big Bang, at the time of the Big Bang. And so it creates millions, I forget the number, but it's more than hundreds of millions of ATP every second. And every cell in our body has, on the average, 2,000 mitochondria and many, many, many of these ATP synthase. So let me stop the screen sharing here for a minute and bring you back. So we now know a tremendous amount about how the particles released from the Big Bang created the atoms and the elements that now have reunited. Little pockets of them have reunited 13.8 billion years later in our bodies to create all kinds of nanomachines that create us, that breathe life into us. And so let me just tie up here with a couple of the takeaways that I had from obviously a much more complex story than this, but you've kind of gotten the broad overview. One of them is that life has profoundly reshaped our planet, particularly photosynthesis and the oxygen that it liberated that completely changed many, many processes on the planet. And particularly, of course, we have to thank it for the oxygen that's now in our atmosphere. And, you know, now people are talking about global warming. And what global warming is doing is it's changing the balance of oxygen and carbon dioxide in the atmosphere. We're removing, insulating carbon dioxide from the atmosphere and warming the planet. Had we not had photosynthesis, which adjusts the amount of carbon dioxide in the atmosphere, our planet now would look like Venus. It would be incredibly hot and have lost its oceans. It's only because we had photosynthesizing life on our planet that Earth has become the hospitable place that it is today. And so, you know, it really brings home to me, you know, the fact that this balance has been created over millions and billions of years that's created the conditions for us to survive. And we really have to preserve and treasure that. You know, sometimes I hear about people who say, oh, well, we're just going to terraform Mars and we're just going to be able to move to Mars. How realistic is that, given that nature has taken an immense amount of time in order to create a very elaborate system here that allows us to live in a habitable place? So that's one thing that I took away from the story. Another thing is that I've come to understand in a deeper way how incredibly complex even the simplest single-celled organism is. You know, and I've now come to realize that, you know, they actually deserve our respect. Of course, we descended from single-cell organisms, and your body and mine is made up of 30 trillion single-celled organisms. We're really each of us is a collection of cells, specialized cells, but they're cells. And so it's given me also a great sense of how incredibly amazing all of us are. We all are. All of our atoms came from the same place. each of those cells in our bodies is more complex than New York City. And so, sometimes when I look around at at other people, I just think, wow, you are really, really an amazing creature. And that's also given me a real feeling of how lucky we are to be here on Earth now at this point in the existence of the universe. Uh, and it's something that I think we should all treasure. So that's my short talk. And Matt, would you like to open it up for questions?
Yeah, sure. I'm just adding myself back here, Spotlight. Yeah, if anybody has any questions, please submit them via the Q&A, or you can do the raise hand function. I can let you. You should be able to talk then. But thank you so much, Dan. That's really fascinating. I love all the illustrations that went with it too. It really ties together the whole story that you're saying. We do have a question that came in so far. Someone asked, how did this morass ultimately evolve into what we recognize as the human form? Further, how do all these theories link to the modern theory of evolution? It's a two-parter.
Um, well, that's those are both big
Big.
questions. But the short answer is that we had single-celled organisms, bacteria and others. Then you had multi-celled organisms. Uh, you had algae evolved, which evolved into plants, and plants spread over the continents. At the same time, you had multicellular organisms in the ocean that evolved, and they were eukaryotic cells, so they didn't have to photosynthesize. They could just eat other organisms or um, uh, or organic matter created by photosynthesizers. And they evolved into worms and into fish and into uh, creatures that swam in the ocean but started living on the edges of continents and ultimately crawled onto land. And they evolved into reptiles and dinosaurs and ultimately mammals. But of course, the only reason they could only do that was because there was something to eat on land, and that was plants, which were again created by photosynthesizers.
Thank you. Another question is, were all of the moons in our solar system formed from or broken off from their host planet?
I'm sorry, what was from broken off from what?
Their host planet.
I don't know the answer to that. It's an interesting question. It may be that some of them were created that were far enough away from the host star that they formed on their own, but I'm not sure I know the answer to that.
Hmm. Um, there, I there was a question I had when you talked in the beginning about like how much salt is like in us that could fill like a shaker and whatnot. How do they um, know that? Um, how do you
Um,
calculate that? Yeah.
I don't honestly know, but I can imagine that uh, uh, they've done kind of a chemical analysis of the percentage of protein and fat and carbohydrates in our bodies, and they've done that for various kinds of tissues. And beyond that, I don't know exactly how they figured it out.
Yeah, makes sense. Um, you had spoken too about like life evolving, some scientists believe it evolved from the surface of the earth versus the ocean. Could you speak more, like I guess briefly, to some of those ideas that exist or the theories?
So one of them which is fascinating, which is the theory that life evolved beneath the ocean. So I should say that there are quite a number of theories about how life might have evolved beneath the ocean. But one of them is very interesting. It's that, very briefly, there's a particular kind of hydrothermal vent, and that what you have is you have gases bubbling up. You have hydrogen gas and other gases bubbling up through the vent, and they create these structures with tiny, tiny little pores in them. And hydrogen is positively charged, or because hydrogen is essentially a proton, which is a positive charge. And so the charges build up in those tiny little chambers. And because there are other gases within them, the charges, the theory goes, create a kind of energy that enables more complex organic molecules to form within those chambers. And ultimately, it snowballs, and you get ultimately the evolution of a cell. That's kind of in cartoon form. The theories about how it evolved on the surface of the Earth are just as complex, because there are a great many of them. Some people think that even that, a asteroid might have created a huge impact, and that there may have been fissures in the Earth, and there may have been water close underneath that created the opportunity for heat, and the impact itself may have created some kind of organic molecules. There's also the theory that the very first life on Earth didn't evolve here, but evolved on Mars, which is not a crank theory at all. In fact, there are quite a number of people who believe it. And the reason why is that Mars didn't have that huge impact that Earth had. And early Mars had oceans. Early Mars had many of the same conditions that we did. And so it might have had longer, life there might have had a longer time to evolve, in part because the early Earth, because of its size, was also impacted much more by huge asteroids and comets. The universe was still forming, and there was all this debris floating around, and part of it's attracted by gravitational pull. So some of these things, or rather just the larger size of the Earth, rather, I misspoke there, would have been a larger target for these things. Some of these impacts might have completely vaporized Earth's oceans before about 3.8 billion years ago. And so some people wonder how easy it would have been for Earth to evolve in the oceans then. But Mars might have been more tranquil. And I did interview a scientist who talked about the possibility, and there are a number of people who think this, that bacteria actually evolved first on Mars, and then an impact hit Mars and ejected, let's say, boulders with maybe bacteria hidden in the cracks of them. Well, we know, because bacteria and other organisms have been found to live for a long, long time on the space shuttle, that those kind of organisms can survive a long space journey. And we know that there are many meteorites that have actually reached here from Mars, rather. If we go to the Antarctic, and scientists collect them. And so one of the theories that's actually, quite well regarded is actually that life first evolved on Mars and then came to Earth.
Wow.
Yeah, that's what I said. Wow.
Yeah, I mean, it's just
Yeah.
wild to believe.
Yeah.
You were talking about like the instance, the organism, like the pores, and maybe this is connected to something, a question that somebody wrote in, how did replication of genetic patterns start? Which may be a big question too.
Well, it is a big question. I'll try to give a capsule summary, but I do have a chapter that's all about that. It's about the discovery of DNA. And this is another question that nobody knows the answer to, but there are a lot of very strong theories about it. There are alternate theories, but one of the most popular is known as the RNA world. I talked about enzymes. Um, enzymes enzymes are proteins, and they can make a chemical reaction that could take 1,000,000 years, wouldn't happen in 1,000,000 years. They can make it happen many times a second. They're that efficient. So in order to have life in a cell, you need something to make those reactions happen fast. And you also need replication, right? Because you need a cell to create some kind of genetic instructions that can create a copy. And I actually interviewed Thomas Cech, who's a Nobel Prize winner, who was one of the first people to discover that RNA, which are DNA is double-stranded. RNA is single-stranded copies of portions of DNA. And he was one of the first people to discover that strands of RNA can, in some circumstances, actually act like an enzyme. And so that's led many people to suggest that the first life evolved in what they call an RNA world, meaning that RNA is single-stranded, which means it's also easier to see how copies of it could be made because bases are complementary. So one base can pair with another base because they only pair in certain limited combinations. And so since RNA can both accelerate reactions like an enzyme and potentially replicate, the suggestion is that was what led to the first cells.
Wow, it's super like mind blowing, some of these ideas. Thank you. There's another question going from a microscopic to a macroscopic, but will the universe continue to expand forever?
Oh, that's a great question. Maybe. So there are two possibilities. One is that the universe continues expanding forever. And then the other one is that the universe will reach a certain point and then it will come back and ultimately essentially create a Big Bang in reverse. And
Wow.
and in fact, you might have a yo-yo effect, right? Maybe the universe is always doing this, expanding and then coming back and expanding and then coming back. But I don't want to get too far afield, but there is evidence that suggests that the universe may continue to expand forever. In which case, ultimately, all matter will end up being stretched out into long wavelengths of energy. But we have, I think, 600 billion years or some amazing amount of time between now and then. So not to worry.
That seems to be it for questions, but do you have any work any things that you're working on right now coming out soon that you'd like to share?
Well, I am working on something else, but it's going to be a while before it comes out. I'm working on another similar book to this one, and it's on the brain. So it's which also turns out to be almost equally large subject matter. But it's about what we know about how the brain works and how we understand it. So stay tuned, but it's going to be a few years before that comes out.
That sounds awesome. Well, thank you so much, Dan. If you're interested in purchasing Dan's book, it's available on his website or likely a bookseller near you, or you can get it from the library. But thank you everyone for all of your questions. And Dan, thank you again for this wonderful talk.
Well, thank you. This was a lot of fun. I really appreciate it.
Great. Have a good night, everyone.